and full professor. In 2007, as a research professor, he became an Alexander von Humboldt Fellow, and in 2008, a Marie Curie Fellow with the Technic University Ilmenau in Germany. Currently, he's working at TU Ilmenau with the Automotive Engineering Group as the coordinator of several European projects that are joint between industry and academia. And he is here today to tell us about the XILforEV project.
Okay, thank you. Good day, everybody. It's a great honor for me to present our project XILforEV, focused on connected and shared X-in-the-loop environment to electric vehicles development. In my presentation, I would like to talk at the beginning how our consortium came to the project concept and which key elements are being investigated in XILforEV. Then 4 case studies will be introduced to demonstrate designing electric vehicle system with the use of proposed X-in-the-loop technologies. Some outlooks to the project impact will finalize my presentation. And let me start with motivation. Since many decades, development and testing of new automotive systems has high demand on efficient validation technologies. However, electrification and automatization of vehicles reveals that traditional combination of simulation and experiments can be not enough to keep common standards of time to market to new products. Where are the reasons? If we take a look at modern car, we can identify that it requires more complex onboard software, even as compared to aircrafts. This fact becomes more critical if we will consider increased share of systems based on artificial intelligence in new vehicles. By taking into account more and more strong requirements to fail to safe operation, industrial companies came to results that pre-production test program for coming generations of cars could be about 14 billion kilometers of virtual, augmented, and real tests. In addition to these factors, electric vehicle design brings some extra problems. Say, higher requirements to the fault tolerance, design measures for better user acceptance, as well as for aligned operation of electric powertrain and conventional chassis systems. Hence, we can identify demand on new design procedures. For our project, the main goal is, in this regard, how we can reduce entire test program. To address this goal, we have proposed an approach with the following idea behind. The most time-consuming aspect in vehicle systems validation is that many iterative test steps are required. For example, by developing regenerative braking control, we need experimental studies on brake dynamometer, electric motor test setup, processor in the loop, and so on. In the practice, relevant experiments are being performed step by step and on the corresponding test platforms. Moreover, it is sometimes impossible that the developer will have all required facilities in the same place. Our solution is maybe quite evident, but nevertheless reasonable. XILforEV approach implements 2 factors. We are connecting by network test platforms from different physical domains and probably situated in different geographical locations. This coupling should allow simultaneous real-time operation and data exchange between test platforms, and they are controlled by a master unit, which involves required real-time models of objects and operating environments. We can expect then several advantages. The first is reduction of validation time. However, maybe even more important benefit is that we can identify in real time certain design problems and phenomena which will be not discovered in the case of non-simultaneous tests. Our approach is not designed from the scratch and was inspired by preliminary studies. So about 15 years ago, American researchers described their experience in connecting two hardware-in-the-loop test setups by internet. However, the communication technologies to this time point demonstrated sensible limitations regarding delays and data losses. Therefore, the consortium partners started similar studies by using the local network as the first step. Here on the picture, you can see the first X-in-the-loop configuration at Technical University, Ilmenau. Stable operation of this approach, as well as improvement of web technologies, motivated us to further feasibility studies. In such a way, we established a real-time connection on hardware test setups between Germany and other countries. With the help of these studies, we have confirmed some years ago that the approach is enough mature to test real-time complex systems. For example, it was possible to run controllers between master test platform in Germany and slave test facilities in the Netherlands, USA, and South Africa. This feasibility study has also identified demand on deeper research and development works towards reduction of delays and dealing with data losses. It has given us an input to XILforEV project. Based on previous studies, as well as considering industrial expectations to electric vehicle design process, we have formulated our project concept. Let me introduce it next. The project is targeting 4 objectives. They are focused on novel technology of connected and shared experiments. This technology is not a simple communication by internet of several devices, but a global validation environment with such elements as machine learning for confident real-time computing, efficient co-simulation with the use of high confidence models, and so on. The project also envisages several use cases which are highly relevant to electric vehicle systems and aimed at design of integrated powertrain and chassis control with in-wheel motors, brake-by-wire, and active suspension. These complex tasks will be not possible without competent consortium. It consists now from 9 partners, including automotive OEMs as Audi, Tier 1 suppliers as Elaf and Tenneco, leading IT developer Siemens Software, engineering company presented by EFS, and finally 3 research institutions, Ivanov, Delft, and Ilmenau universities. In addition, we have several associated partners in Japan, Russia, and South Africa that allows increasing global impact from our research. To the start of the project activities, Technical University Ilmenau, as the coordinator, had already an established network of different test platforms. You can see here an overview of available facilities. The test setups are placed in different buildings within the campus, and can be connected with each other by optical line or by VLAN Wi-Fi. Of course, for XILforEV concept, we need a limited number of devices. For the project task, the first local connection consists of 3 platforms: motor test bench, brake dynamometer, and electrohydraulic brake hill. These test setups are distributed on the distances most at 1 kilometer. This local distributed testing environment has extra a cloud-based real-time full vehicle model in AMSIM software. It makes possible that all test platforms receive the same parameters of the maneuvers and driving conditions. Next step is to connect local laboratories with experimental facilities of other partners. Hence, we are receiving distributed remote XILforEV test environment uniting Ilmenau, Zaragoza, Delft, and Ljubljana. The connection is, of course, established by internet. These 4 hosts shaping the core of XILforEV community. But from the project start, we are also establishing connection to other locations in different countries. Both local and remote environments include not only test setups themselves, but also many important inherent components. Therefore, let us take a look at key elements behind of XILforEV concept. The XILforEV architecture can be represented by 4 layers, which can be replicated to any test or simulator platform included in the experimental environment. The bottom layer or gateway includes signal routing that ensures the interaction of test setups in the network. In our case, they relate to the VLAN. The gateway has demand on a proper communication protocol. We decided to implement user datagram protocol or UDP. Each test setup can have individual control software. Other software tools are used for full vehicle model and electric vehicle systems controllers. Therefore, next layer is responsible for co-simulation interface. In our project, we are using FMI or functional mockup interface, which is the popular industry open source standard for exchanging models. And then on the top, we have an application layer where the vehicle systems are represented either by hardware or by real-time models. Our particular interest is the configuration of the communication layer. We have established separate virtual private network, VPN, for all test setups included in the environment. Each test setup has unique IP address. The main server is based in Ilmenau, but the testing platforms in other cities and countries are also recognized in the established VPN. During the real-time joint experiments, it's important to synchronize the timing between the participating hosts. For this purpose, we are using LeoNTP time server with high accuracy. This guarantees that the testing maneuver will start simultaneously on each experimental platform. I believe that one of the most demanded questions from your side is how sufficient are modern communications for real-time experiments? Let me give you a short example. Of course, communication delays can negatively influence the results. It can be seen on the left figure. It illustrates that the size of macro steps can bring different outputs even for a relatively simple quarter core model. We have identified that for electric vehicle systems with the control on motors, brakes, and chassis, the delay should be within 125 milliseconds in average. It will be sufficient. In addition, we can classify this area as hard, soft, and near real-time. For instance, the brake control can require hard to soft real-time. A slower active suspension can work in the near real-time area. Our test shows that most of our hosts of interest satisfy the real-time requirements. For intercontinental hosts as New York, Tokyo, or Pretoria, the conditions are now not so sufficient. However, even here, the XILforEV approach can be used for the design tasks without strong requirements to real-time. For example, for some automotive systems with preview or predictive control. The term real-time is crucial not only for communication, but also for co-simulation. In our test, we are using 4 types of software: AmiSim, MATLAB Simulink, internal software of test rigs, and visualization software on the driving simulator. Their interaction is organized via FMU, functional mockup units. This approach is widely accepted by industry and gives us enough flexibility for co-simulation tasks. The co-simulation is closely related to the continuous integration of experimental and simulation data. This part of our XILforEV environment has been established on Polarion tool with the support of our partner Siemens software. Our solution can be efficiently transferred for further applications of XILforEV concept by industrial partners, and then properly address joint testing programs between OEM and several suppliers. OEM supplier communication by the development of new systems is also covered by our traceability concept. This extends the proof of concept demonstrators and can be also augmented to the development process of physical models. The models are also in the focus of our project because many conventional approaches to vehicle modeling are not suitable for real-time tasks. Therefore, we have put particular attention to reduced order models design, which will guarantee the high level of multi-fidelity. In our case, reduced order models are continuously updated with the test data. This feedback is organized with the help of original methodology from our partner Ilmenau, and the proposed methodology combines data-driven and machine learning techniques. In XILforEV environment, the reduced order models not only simulate the vehicle systems, which are not present in the validation as the hardware, they have also another important function to compensate communication delays or missing or lost data. So, I have overviewed key elements of the XILforEV environment. All the components are from IT and communication topics, and you can reasonably ask me, where here is the relation to electric vehicle systems design? To answer this question, let me introduce 4 use cases for which the proposed concept is applied. The first use case, brake blending. Only this use case is being tested in local shared environment. It means that all the test setups are situated in the same host campus of Ilmenau University. These 3 test rigs are participating here. Motor test rig, brake dynamometer, and brake system hill. The real-time model on the vehicle dynamics and its other systems are made in AmiSim. What we can extra investigate with XILforEV environment as compared to conventional brake blending design procedures. Firstly, we can optimize the controller by such important parameters as real motor dynamics and thermal behavior. Secondly, we can deliver the information about brake friction, that it almost not considered in non-brake blending systems that can lead to under or over performance in the brake controllers on real vehicles. The next use case, ride blending. This case is dedicated to novel patented technology from Tenneco, which is not available on the market yet. The idea behind the ride blending is to use electric motors also for vertical force control and to integrate it with the active suspension. Therefore, the main platform here is the suspension test bench in Zaragoza. And this test bench is connected to driving simulator in Delft, where the impact on ride blending on the driving comfort can be evaluated. Other vehicle components are simulated in real time as before on the server of Ilmenau University. The most complex use case. Here the brake and ride blending are being integrated with other control systems as ABS and torque vectoring, and then overall effect on the vehicle dynamics can be investigated. 3 different hosts, Ilmenau, Zaragoza, and Delft, are involved. Nowadays, most of design cases for the integrated chassis control are based on pure simulation studies, and the important actuator constraints are often ignored. The availability of a vehicle demonstrator with all installed active systems is also low. Hence, in our opinion, the XILforEV concept is probably one possible and proper solution to investigate integrated chassis control with real hardware components. And we should not forget that electric vehicles have increased requirements to fault-tolerant and robust operation. Therefore, our final use case is dedicated to the fail safety. Probably the most critical component of the electric vehicle in this regard is the motor. In our project, we are using the newest generation of in-wheel motors of Elaphe, which have in any case high level of reliability. Nevertheless, their operation can be influenced by external factors and other systems, especially in context of integrated chassis control. In this regard, the powertrain test rig is connected with other platforms, including the driving simulator, that allows analyzing impact of motor faults on the overall vehicle operation and driving dynamics. Finally, to use cases, I would like to say that plug-in concept of our XILforEV environment makes possible inclusion of other test setups, and more use cases can be emerged as well. Now, a few concluding remarks. What we are expecting from our project? First of all, industrial participants of the consortium expect a considerable reduction of lead time and time to market for new electric vehicles and their systems. This will also contribute to increased market penetration of electric vehicles and improving development efficiency at minimized costs, thanks to more compact and efficient testing and validation procedure. Our approach is also not limited by electric vehicles and can be transferred to other cross-domain applications. But the project has not only industry-related impact. The concept of XILforEV is a clear illustration how the remote collaboration of engineers and scientists can be organized, especially in our hard times. Many researchers across the world could have great ideas, but very limited possibilities for their experimental validations. Sharing of test platform, inclusion of external laboratories, real-time data exchange, all these factors can definitely make our global research process better. If you need additional information about the project or seeking for potential collaboration, please contact me. My presentation is over.
Okay, excellent. Thank you. So we have a few questions here that I'll raise. So the first question is from Abdullah Derevo, and it's a question about the impact on the simulation time of FMI or FMU, and also is there an importance related to that? Related to the time of transfer between two locations, you know, does it change with greater distances?
Okay, good. I would like to answer about impact of FMI, FMU. We have compared this with other co-simulation standard which we have previously developed in another project, and it is now standard also in Mandelic Association. I will say there was a low influence of co-simulation interface on real-time applicability. I don't know how it can be in different design tasks, but in our case, we will consider development of control on electric vehicle powertrain and chassis. FMI, FMU are absolutely enough. Good. And then the question regarding transfer of information between, in our cases, in real configuration, test rigs are situated in Europe. I will say in critical cases, we observed delays maybe between 40 and 100 milliseconds, but for our task it was not seriously critical impact because it was quite comparable with the processing time on the hill. In some cases, if there is longer delays and longer distances, it can be the issue that we need then in models extra estimators to try to predict expected behavior of object if the connection will be too low or data are missing. But as I said, for example, between Germany and Japan, Ilmenau, Tokyo, we tested ABS controller, two ABS controllers on two vehicles, and even in this case, delay was acceptable.
Okay. I have a pair of questions from Abdullah Pam. The first question is about comparison of local hardware in the loop testing versus the remote hardware in the loop testing. Have you done any side-by-side comparison to see how they might differ as far as the results?
Yes, of course, local is quite easier, can be established quite easier, and there is no, I will say in local network, almost zero delays, only typical delays comparable if for example, we are using only hill and computer. But we will do next year a comparative study, the same use case for the base braking control will be tested firstly in local environment in Ilmenau, and second step will be in remote environment by connecting one test rig in Ilmenau, second in Ingolstadt in Germany. And then maybe I can give you more data next year about comparative analysis.
Okay, excellent. Another question in from Adrian Genick about whether the timing delays can introduce instabilities or potentially feedback into the system behavior?
Yes, this danger exists. We did not observe it at the moment, but we expected therefore in our approach for the machine learning, and we will extra take it into account. I mean, these methods I mentioned in my presentation, or reduced order models, not only should make real-time application better, but also should compensate these issues. There is also another ways of compensation. For example, we can use some kind of the filters or estimators extra. I will say we did not observe this fact, but the solutions are available.
Okay. And then let's do one final question, and that is a question about limits to scale. Are there any upper limits on the scale, the number of components you could connect, the number of locations? Is there some practical limitation?
It's also maybe limited by performance of VPN. I mentioned that we are using VPN. It is the most efficient solutions. We have established in campus separate VPN for XILforEV activities to redistribute IP addresses to the partners. I will say several dozens of test platform or computers can be integrated from the side of VPN. I see a reasonable number can be up to 10 and maybe more. This is more, but VPN, maybe I'm wrong, even maybe give possibility to inclusion about the 50 platforms or even higher.
Okay. We have one more question that just came in. We'll do this one and then we'll stop for real. That's from Ashkan Peruz asks, other than delays, have you considered bandwidth limitations for the long distance XIL within the VPN, and could this have an impact on performance?
Yes, I will say again, we have expected it. We have observed a few limitations, especially by intercontinental connection. But I will say were for us applicable. So it was no considerable influence on results. I will say again, it depends also on the task, on control task. If there is high speed task, for example, vehicle stability control like ESP system or ABS, the bandwidth, if will be the problems with bandwidth, it should be compensated. But the task can be also of slow speed. I mentioned it, for example, if some system would like by radar receive information about environment, some kind of prediction. This is not so high-speed process like ABS. In this case, the bandwidth limitations will play not so much role.
Okay, great. Okay, well, thank you. I guess everyone can thank our fourth speaker with our private applause in individual offices. And at this point, I'd like to invite all the speakers